All right, now we're going to do our free response section. So, again, I tried to get a nice wide variety of topics for us for our P2 exam. I thought these are all pretty fair. So I would say these are definitely on the easier side, but it does assess kind of all the main domains of the course. So this gives a good check kind of what areas you need to work on. Alrighty, so first we got some electrostatics. We got some particles here. So we got some two small spheres. They're equally spaced along the x-axis. And we have a small test charge that's placed on the y-axis. So we can maybe start to be getting a bit suspicious because I notice that my coordinates are looking very Pythagorean theorem friendly, but we'll get to that. So again, for the mathematical reasoning question, this is part A. There's two subparts. There's deriving, and then there's a picture. So here we actually lead with the picture, which means that this picture should help us do some sort of a derivation. So it's always helpful to read all of part A first. So we want to draw the forces, not components, exerted on the test charge by each of the spheres. We want to represent each force by a distinct arrow, blah, blah, blah. So this means don't draw F net. We want to draw the actual forces. Then we want to derive the expression for the net force F due to all the charges. And then we're on to part B, which is modified. So think of part A and B as their own little subproblems. Alrighty, let's do it. So this will involve superposition. So we have my purple sphere, and the test charge is positive. So like charges repel. And same idea over here with my blue sphere, also positive. So like charges repel once more. So now we can see what's sort of happening. Is we can see that we have this sort of horizontal symmetry. So we're going to get this sort of net force that's going to act directly upwards. So when drawing our forces, we're just going to draw everything nice and symmetric. So starting on my dot, I might draw sort of two right and two up, and then I might draw two left and two up. So these are just the two forces. And notice that I know this is going to work. I know this is going to work out nicely because we see that the horizontal components cancel, right? Two left and two right. And the vertical components add. So how did you get your points here? Well, to get your points here, it's worth 2, the diagram on the MR. Your first point was for anything with horizontal symmetry. And then for A2, you had to have a net force up. So that's how you got both of your points there. So by horizontal symmetry, you actually had to draw something with non-zero horizontal component on each one. So you couldn't draw two up arrows to get point A1. A1, I believe I specifically said you have to draw two diagonal forces whose horizontal components cancel. So if you just drew a direct arrow up, you would get A2, but not A1. All right, now let's derive an expression for F. So the diagram was supposed to help you here. And how does it help you? Well, it tells me who is causing the net force. Because what is the net force? Well, we know that the net force is being caused by two spheres. And it's not all of the force from each sphere, it's just their y component. So that's the point of this, right? That's why I made you draw the diagram first, so that you can understand that the net force is just going to be two copies of the y component. So now we can just do some Coulomb's law. Because we know that if we're just doing our usual like polar angle idea, we can just take the full force from one of the spheres and tack on a sine theta to get our vertical component. So let's try to draw that out because we have a coordinate system here. So I'm just going to draw one of these sort of triangles to help us out. So in our picture, I'll draw this. So what we were given is that this distance, this horizontal distance, was 3a, and then this vertical distance was 4a. Oh, how interesting and convenient. And then, of course, for Coulomb's law is about the center-to-center distance between these charges, so we're going to have to use Pythagorean theorem. So we can see that our distance r here is just going to be the Pythagorean length. 3 squared plus 4 squared, all under a square root. Wow, what a surprise. It's a 3, 4, 5 triangle. Come on, you knew I'd do this to make your answer look nice. I try to make it convenient, right? So we got a distance of 5/8. So then we can just apply Coulomb's law, because we said F is equal to 2 times F sine theta, where F between the two charges would be K, Q, Q divided by R squared. And then we're multiplying by this sine theta component to get the y. And what is sine theta? Well, sine theta is defined as opposite over hypotenuse, where the opposite is 4a and the hypotenuse is 5a. So I could actually leave it like this, and if you're kind of scared to mess up, you can totally just leave your answer like this and get full points. But this does simplify to 2 times kqq over 25a squared times 4 over 5, which is equal to 2 and 4 make 8, 25 and 5 make 125. So 8 over 125 kqq over a squared is our rubric final answer. So how did you get the 5 points here in this derivation? Well, you got 1 point for a sort of multi-step derivation that involved Coulomb's law. So A3 was the multi-step point with Coulomb. So if you have more than one step and tried kqq over r squared, you got that point. A4, you got A4 for understanding that there were 2 spheres. You got A5 for understanding that, for attempting to extract a component. So even if you pick the wrong one, that'll get you later because you'll just get the wrong answer. I'm trying to leave some space here, but I guess we'll just scoot that over. Then for A6, to get A6, you actually got a point just for saying the Coulomb's law distance was 5a. So any sort of Pythagorean theorem involving the 3, 4, 5 triangle got you that point. And then all the plug and chug and the substituting got you A7 for that correct answer. So I thought this was pretty fair to pick up a lot of points. So again, you got a multi-step derivation. You got a point for showing that there's 2 contributors to this net force. And then you had to extract a component somehow by doing a substitution for a trigonometric factor. So you could have, by substituting something in for sine or cosine, you got that point. And you get a point also for just the Pythagorean distance before the answer. All right, now part B. So this is where P2 is different than the C's. So the physics C's do an like alternate derivation here. But P1 and P2 we're asked sort of a conceptual claim, and we have to justify it. All right, suppose the test charge is released from rest while the 2 spheres of charge big Q remain fixed. Indicate whether the potential energy of the 3-charge system increases, decreases, or remains constant once the test charge begins to move. So there are 2 main ways of approaching this. I'll talk about both, but I'll show you kind of the easier one. So first of all, we got to play this out in our head. What's going to happen if I release the test charge from rest? Well, it's going to fly upwards. So again, realize that with the justifications for AP Physics, you are not trying to convince us. You're really saying, can I cite the proper physics facts for this scenario that are going to tell me what the choice is? So I always do the checkbox last. So I'll start just by saying the simplest thing I know about this scenario. Once released, the test charge begins to move. Now, this technically isn't part of the rubric, but that's a good starting point, right? That's just the fact of the scenario. That's what happens. The test charge moves. So, if we're talking about energy, well, I know a type of energy that involves motion, right? This means, so the kinetic energy increases for the test charge. But you can't just gain kinetic energy in a closed system for free, right? That has to come from somewhere. So also, since k plus u equals constant, if the kinetic energy of the test charge increases, the potential energy associated with the test charge must decrease. So energy is conserved. I shouldn't say so. I should probably say because. So that was my intention, is that you can just tackle this from like a real quick energy point of view just by saying, oh, kinetic energy goes up. So how did you get these 2 points if you tackled it with energy? You got energy. You got the energy point for B2. B1 is the checkbox. By saying kinetic energy increases. And then you got point B3 by stating energy is conserved. Now, there's another way that you could do it, where if you did an alternate solution, which we might put on the side here, we might also say that U is equal to the sum of KQQ over R. So you can say that the test charge moves away from the spheres. So U decreases since R increases. So this is another way that you could get the points, and I might guess that a lot of you picked this way. So you get a point actually just for saying that like the distance from the test charge to the other 2 spheres is increasing. That gets you B2. And to get B3, you have to just reference that potential energy is going to be decreasing if R is increasing. I think in the rubric I originally said you have to say that the potential energy is positive, but I don't know if I like that. So we might retroactively change it just to say that you have to say that the test charge moves away from the spheres, or you have to reference like a relevant potential energy formula. So I think just citing this formula along with moves away kind of counts for B2 upon further analysis. And this is definitely B3, is just saying that we have this inverse relationship. So I didn't think that was that bad. This was a pretty good electrostatics review. Like this covered a lot of the unit, whatever. I always forget what it is in P2. But this is a lot of the unit there. So I'd be interested to see if there's like alternate explanations you have for B. I'd be interested to hear them. These 2 I think are the main the main families of them. But there's also one I considered putting on the rubric with potential, but I didn't think enough people would do that one. All right, so now we'll move on to our TBR. All right, now we're on to our TBR. So the translation between representations, this is our 12-point question. This is the one that tests the most skills. I don't think it's the most difficult. I think usually the mathematical routines is the most difficult. But the translation between representations, as the name implies, we just test all these different skills. So we look at a scenario from a bunch of different perspectives. So a good TBR generally doesn't tell a story, but instead it makes you look at the same problem from different perspectives. So it's always beneficial with these TBRs, or any question for that matter, just to read the whole thing first, so we understand kind of what the objective is. But that's ultra important for the TBR because we're looking at these different perspectives of the same scenario. So based on the picture, this shouldn't look unfamiliar, right? This is just our classic bar rails system. So we know this is going to be magnetism, Faraday, motional EMF related. So we are moving a conducting bar at constant velocity along a set of U-shaped rails. And we're given this sort of time description here, where it starts without being in a magnetic field region, then we drag it through an out of the page B field, then there's an into the page B field, and then there's no B field. So part A wants us to draw the direction of the induced current, if any, at each of these times. Then part B has us derive an expression for the power dissipated by the bar at a certain time interval. Part C wants us to graph the magnetic flux through the loop bound by the bar and the left side of the rails. And D just asks us the classic consistency question. So theoretically, we could do these in different orders because it's just really 3 unique ways to look at this bar rail problem. But first, we're just going to do A. All right. Draw the direction of the induced current at each of the following times. If the current is 0, indicate that. Well, first, at t equals 0 to t equals 1, capital T, we see that our bar is, there's sort of 2 ways of approaching it. One way is using the Hall effect, where if we do our QV cross B on our bar, we'd see that positive charges would be collecting on the bottom of the bar at this time, which is going to create sort of this mini battery that's going to look like, it's going to look like this. So essentially we've turned our bar at this short time, we've essentially turned our bar into a battery like this, and this is going to generate a clockwise current. So using the Hall effect, we could see we're actually going to get a counterclockwise current through the circuit. Or the way that most people are going to approach this, which is the intended way, is that you look at this with a Lenz's law approach. So notice that from 0 to capital T, I'm sort of entering a B field where I'm getting more and more circles. So Lenz's law says we always generate a current to fight the flux change. So I'm getting more circles, more circles, more circles. So I need to generate X's. And if I do my right hand rule, that is a clockwise current. So clockwise and through the bar would be down at this time. Then we're going to get the opposite direction of current because now instead of more circles, we're getting more X's, right? So if I'm getting more X's, I need to generate circles, which would be counterclockwise. Which makes sense because our sort of flux change is reversing sign at that time. And then when we're out of the magnetic field, well, there's no flux change. There's actually no flux through the loop at all because these regions are equal width. But there's actually no current because I'm not sort of, the bar isn't gaining any sort of additional magnetic field in the loop enclosed by it. Right, once the bar is over here, it stops sort of gaining new field in its rectangular loop. So how did we score this? Well, B1 was a downward current on the first bar. B2 was opposite currents at the first interval and the second interval. Because even if you got the right hand rule wrong, we wanted to reward the fact that the test taker recognized there's a sort of opposite effect. And then B3, why am I calling this B? This is A. Then A3 was just for saying I equals 0 at 2t to 3t. Because I thought that was worth a point there. because your diagrams were 3. All right, the bar has length d and resistance r between the rails. Derive an expression for the rate p of energy dissipation on this sort of first interval. So we know we're going to have some sort of power dissipation because our flux is changing. And that's going to cause a current, and we have a resistance. So we know that we need some sort of power dissipated. Now, there is a sneaky alternate approach that we can talk about because we have time. But we know that if we want power, this is the formula sheet version of power. So I'm going to deal with this one. If you know the shortcut formulas like I squared R or V squared over R, that can simplify a step for you. So we need the current through the bar and the potential difference across the bar. And the first step is recognizing that this is a motional EMF problem. So we had to figure out that delta V was the Hall effect voltage, which is just VBL, or in this case, VBD. Then we had to recognize that the current was just going to be the induced EMF divided by the resistance, which is VBD divided by R, so using Ohm's law there. So power is just going to be VBD times VBD over R, which is equal to VBD quantity squared over R. So really, I didn't do too much with this derivation. I tried to make this a quite easy question. So you actually got points for any sort of multi-step derivation. So B1 was some sort of multi-step Ohm's law, Faraday, motional, etc. B2 was for identifying the induced EMF is VBL. B3 is using Ohm's law. And that counts. Using a power formula that uses Ohm's law counts as well. So if you used power equals EMF squared over R, that actually gets you B3 because that's applying Ohm's law. And then B4 is the answer. So pretty easy to pick up some points here. Now, I did say there's like an alternate solution. Now, I highly doubt anyone did this because this is, I don't know why. I don't know why people would do it this way. But you could also have found the power input by the external force. So we could have said that power is equal to force times velocity. And the force is the magnetic force acting on the bar, which is BIL or BID in this case. And you could solve for the current using VBL over R. Or sorry, VBD over R. And notice you do get the same answer because you square B times I times D times V. So you get the VBD squared over R. You could have done that. I don't know why you would, but it does get you the correct answer. So there is that. All right, sketch the absolute value of the magnetic flux through the rectangular loop bound by the bar and its left end. So essentially we're saying like just draw the most natural loop, the sort of circuit loop created here. Well, I start with 0 magnetic field piercing this rectangular loop, right? Because at t equals 0, I have this object. Then at t equals 1t, I have this object, which has circles piercing it. So I know my flux increases. Then, once I've reached 2t, I've enclosed exactly the same amount of magnetic field, but in the opposite direction, so the fluxes will completely cancel out. So we know that if I were to segment my graph, I would have 0 flux here. I would have maximum flux here. and then I'm back to 0 flux here. And then we know that once you've canceled these magnetic fields, there's going to be no flux. So how do we do this? Well, it's constant speed. So the fact that this was a constant speed tells us that our connector should just be linear. And this isn't the best linear I could come up with. I think I'll have to mess with my line tool here. We'll make this solid. Make you solid as well. So this is our correct graph. So this is how you get the points on the graph. C1, linear increase. C2, linear decrease. C3, 0 everywhere else. Is our graph consistent with the current arrows? So I usually think that D2 on the TBR, no matter how easy the question is one of the hardest points to get because we are not looking for the correct justification. We're looking for referencing the correct functional dependence relationship and the correct representation. So you can't just say consistent, current opposes flux change. You have to reference this graph. So D2 boxes you in. You have to answer specifically what they tell you to. I see so many great justifications that get 0 points on the TBRs because we're not referencing the feature. So you do have to say consistent or not consistent. The fact that we're seeing this video means I did not mess up and I made a consistent graph. So why is it consistent? Well, you should always start out just by saying what the physics fact is and how to connect that with our graph. So we have flux and we have current. So what is the relationship between flux and current? Well, we know that induced current generates a B field to oppose flux change. This is true. This is a great statement. This explains how you got your current direction. 0 points. We have to connect this to our graph. So how do we know that our current directions are consistent with our graph? Well, notice it's about the flux change. So I have an increase in flux from 0 to t, and I have a decrease in flux from t to 2t. So we notice that since the slope of the flux graph has opposite signs on the two intervals we're looking at, the current directions should also be opposite at those times. The current directions are opposite on those intervals. So this is a pretty precise justification, and you really needed to say something super close to this to get D2. Now, if you made some totally wonky graph and said inconsistent, that's fine too. But you had to reference how the induced current relates to the sign of the slope. So you needed very specifically to talk about the sign of the slope. So I have opposite current directions at these two times, which if I have opposite current directions, that must mean my flux changes are in opposite directions at those times. And what is rate of change on a graph? Well, that's slope. So you had to specifically talk about like having a positive slope and a negative slope, for example. So you didn't even need to say Lenz's law, actually. This is 0 points. It might help you make your explanation, but you had to say the flux graph has opposite slopes or something about the sign of the slope. So if you said anything about current direction is related to sine of the slope, that gets you D2. So I thought this was a pretty fair TBR. Like, this is about as chalky as I could go with the bar rails system. There's certainly some like harder variants. Like, I could have asked you the magnetic force on the bar, which it actually isn't that much more work, actually, right? And it's actually right here. But we're trying to give you points, right? You're doing quite a few things here. So trying to make it fair. All right, lab question. This should be mostly free. In experiment 1, students are asked to use a linear graph to determine the index of refraction, Ng, of glass. Assume the index of refraction in air is given by n air is roughly 1. So this definitely looks like we got Snell's law, right? Index of refraction, air, glass. Students have access to a laser pointer that emits monochromatic light in a single direction, and we have a protractor. Okay, well, a laser pointer is just an apparatus. You can't measure anything with a laser pointer. So remember, the part A of this lab is what can you measure? And of course, it's going to be at least 2 things. So I can't measure anything with the laser pointer, right? A laser pointer is a device. So you don't actually have to write a procedure. But again, this is our just classic Snell's law lab. So what do? Well, we just shine our laser pointer at the piece of glass, and then we'll see that it bends. And what we want to find with our protractor is we, of course, are measuring 2 things. We're going to measure our theta I, our incident angle, and we're going to measure our theta R for our refracted angle relative to the normal. So all I have to say, what can I measure? Well, I have a protractor and a protractor only. So I can measure angle of incidence, theta I. I can measure angle of refraction, theta R. So I always like to organize my lab response as a bullet point for each of the graph quantities. So like I know I'm going to transform these 2 variables somehow. And maybe I'd write like some other thing to measure, like if there's a constant I would need. But I always just like a bullet point. So this is not a procedure. Notice I didn't say, shine the laser pointer above the light at some angle. Do this, do this. We don't care. This question is not about designing an experiment. It's really just about your science skills here with some physics connections. How can we reduce uncertainty? Oh, I don't know. Do multiple trials. So how do you get this is the same for like any lab question, right? We can just say repeat for multiple angles theta I. Do multiple trials. You could do other like more niche things like zero the force sensor, but please just do multiple trials. That's all we're looking for. These aren't physics points, these are science points. All right, how can we graph this? Well, we're talking about refraction. So of course this is Snell's law. So it was between air and glass. So I know I can do n for air times sine of theta for air is equal to n in the glass times sine of theta in glass. Okay. And we were given that the index of refraction in air, we could just approximate as 1. So we can say that our air angle was the incident one. So we can say sine of theta I, 1 times that, is equal to Ng times sine of theta R. So we can see what we're putting in our boxes, right? We can put theta I as our first variable, and that is surrounded by sine. And theta R is our other variable, and that's surrounded by sine. So we are graphing sine theta I versus sine theta R. It is important that you say versus, or you just draw the graph. I'll show you actually just the best way to get both points. That's just the easiest. It's basically doing this. But you can't, well, actually, you can get the first point by saying and, but that makes it hard to figure out what your slope is. So notice that if I do this, where we have sine theta I equals ng times sine theta R, we said sine theta I was our y, sine theta R is our x, so this means ng is our slope. So this actually earns B1 and B2. If you just wrote this, which I think is the best response, you get both B points. This is as simple as it gets. It is so clear to us what you're putting on the axes, and it's very clear what the slope is. If you wanted to write it out in words, you'd say graph sine theta I versus sine theta R, and the slope is equal to n for glass. So how do you get B1? Pick a correct set of axes. Doesn't matter the order. And then B2, you need a correct slope relationship. So again, you got A1 for saying you measured two different angles. You can't say measure the angle. You have to say that there's two angles being measured. A2 is your uncertainty. Although, if you're claiming to have multiple angles here, in the past we've given you that point, if it's clear that you meant to measure two of them. All right, now on to our unrelated experiment. That's the you gotta do it one. In experiment 2, the students are asked to use a graph to determine the work function phi of a metal. Well, there's literally only one equation that involves this setup with a work function, and it was notably absent from our multiple choice, so here it is. Now, what is the work function? Well, this is our photoelectric effect. You need to be able to recognize this diagram as the photoelectric effect. So what is the photoelectric effect? Well, it says the students shine monochromatic light at a plate, and they measure the maximum Ke of the ejected electrons for different frequencies. And again, there's also this added thing where the frequency has to be high enough or you actually don't get ejected electrons. That's where this work function comes into play. You can think of it as sort of a startup cost that gets electrons ejected in the first place. So what is the photoelectric effect? Well, the photoelectric effect says that the kinetic energy of ejected electrons is equal to the photon energy, HF, minus the work function. And we don't really have to transform this at all. So we were given frequency and kinetic energy, so we just use our photoelectric equation. And this is actually kind of an interesting lab question because we're actually solving for this work function. So we still do business as usual. We're trying to linearize. So notice I can definitely just put kinetic energy in a box. H is Planck's constant, so it is a constant, times the frequency, so that can go in a box because that was a variable, and then minus the work function. So what is linear? Well, I just plot the raw data because kinetic energy is going on our y-axis, our frequency is going on our x-axis, and we actually get a y-intercept that means something. That's actually what we want. So Planck's constant is the slope, and negative of the work function is the y-intercept. So, as per usual, I'm just going to stay here. We snap our fingers and do the mining off camera, and a funky graph is spawned in. So here, actually, I didn't use the grid just in quadrant 1 because I wanted to show you that you can actually solve this without linear regression if you just estimate where the y-intercept is. So this is why I get this weird looking graph. So that like 50% of the grid rule is kind of outdated. Now, I don't imagine you'd get a graph that looks like this. Usually we're going to give you the strictly positive graphs. And also realize you're going to get some non-physical behavior, right? Because I can't have an electron with negative kinetic energy. So that's why this is sort of representing our cutoff frequency for where the photoelectric effect starts to actually eject electrons. But we can extrapolate this best fit line to figure out where that point is. So notice I scaled my axis. I have my kinetic energy in EVs. I have my frequency in 10 to the 15th hertz. And I actually did do my linear regression. But first, let's show you how you get the C points. So to get the C points, C1 is the linearization. So you had to pick something that's linear. You didn't have to transform anything for this one. C2 is the axes / units / scale. So you had to name your axes, you had to put units on them, and you had to have a linear scale on each. C3 was for plotting the points. It's very rare someone loses C3. And then C4 is obviously our best fit line. So you could have graphed utter nonsense and you'll get C2, C3, C4. So that's why I say you should be getting at least 5 points on the lab, even if you know nothing. No physics at all, you should be getting the 5 points. Because you can get 3 of the graphing points, and you can get the measure / uncertainty point. Then for D, we just got to calculate the work function. Well, we said that from our linear model, we said that K was equal to HF minus the work function. So we said that this object was the y-intercept. So the y-intercept is equal to the negative of the work function. So the work function is just going to be the negative of negative 3.1, so positive 3.1. And what's the units on that? Well, it's just going to be whatever the units are on our y-axis. And this is an energy, so it is EVs in this problem. And we can check that that is consistent with our drawn regression line, because if I count 1, 2, 3, looks to be just a little bit beneath 3. So 3.1 seems reasonable that this line could go through that point down there. So how did you get the D points? Well, you had to relating to the y-intercept gets you D1. The correct answer gets you D2. Now, since the answer is the y-intercept, if you just spawn in the work function, this is like one case where you get both D points just from an answer. So if you have to do no math and your answer is just the slope or just the y-intercept, you can get both D points just by spawning the answer in. And now, I didn't have to be this nice, but I thought it was reasonable to not take off points if you said negative 3.1 EVs. I might change that, but I think that it was the point of the problem was to recognize the y-intercept. I didn't really think knowing that the work function was non-negative was important here. So I thought this was a pretty standard lab question. So you see that I'm really trying to fill in all the gaps that weren't in the multiple choice. So there wasn't a whole lot of Snell on the multiple choice, and there was no photoelectric effects. Just like there was no moving bars, or there wasn't too much Coulomb's law. So tried to get a balanced exam here. So this means that our last topic is going to be another one we didn't do too much of. And we did nothing actually with specific heat. So I saved that for the QQT. This is actually my favorite problem on the test. I really like this QQT. These are always my favorite. I just like doing the QQTs. It's really just good physics, right? Being able to do stuff with and without math. So we have these two liquids. One of them is at 0 degrees in some temperature scale, and one of them is at T0, which is greater than 0 in some temperature scale. The liquids, we have the same like mass, they have the same density, so they're going to mix. The only difference is that, so you might want to say that this is sort of our cold liquid, and this is our hot liquid. The only difference is that the hot liquid is a material with twice the specific heat of the cold one. So we're going to mix these together in one container. It's an insulated container, so we know that any transfer is just going to be confined between the two. And we want to compare this sort of equilibrium temperature to the midpoint of the two. And it might seem kind of random that we're comparing it to this, but like if you see this, you can say like maybe pick a number, like pick a number for this T0 if it helps. So like if T0 is 100 degrees, so if I mix a 0-degree liquid with a 100-degree liquid, if I mix them, your first thought is going to be, oh, I'm mixing 0 and 100, so it's exactly in the middle, 50 degrees. But these specific heats aren't the same, so we have to determine what that is going to do. So as per usual, I think it is easiest to start with the facts, then do the checkbox. Because again, the QQT, we're not trying to be convinced. We are trying to see if you can cite the specific physics facts. So let's see that. Well, what do we know about mixing problems? So I'm hoping that we've seen these sort of mixing liquid problems before. So anytime you have an isolated system, so we have this insulated container, that means that any heat transfer is only between the liquids, right? The surroundings does nothing. So what we know is that since this is isolated, we know that all heat transferred to liquid X, right? Because we know that X is going to gain energy from Y because it's the colder one. All heat transferred to X comes from Y. So that's our first fact. And that's going to be really helpful when we do the derivation. Also, this is one where if you're really confused about it, the part B, I should have done what I said and read all the parts first. Part B asks us to find the total energy transferred to liquid X from liquid Y in terms of the variables. And part C is something different. So it's not a is it consistent one. I tried to do one is it consistent per FRQ set and one like modification. So we know that all the heat transfers to X comes from Y. So this means that the Q is the same. Okay, so heat is the same. So the energy transfer between the two has the same magnitude, or absolute value, I should say. So why is that helpful? Well, Y has a larger specific heat. So you get less temperature change for the same energy. Because again, we're not deriving an expression here. You can definitely reference equations. We just don't want you to be deriving. So we have Q equals mc delta T. So what we're saying here is that Q has to stay the same. So the Q between the two liquids stays the same. So if liquid Y has a larger specific heat, and the mass was the same, we must have a lower delta T from Y to get the same energy transfer, right? Because if C tells you how difficult it is to change your temperature, I like to think of it as like temperature inertia, right? It's how hard it is to change your temperature. So if it's harder to change liquid Y's temperature, and we have the same sort of input, well, this means delta Ty is going to be less than delta Tx. So our final equilibrium temperature is going to be closer to Y's temperature than X. So Tf is going to be larger than the midpoint. Also, this is nice to think about in terms of extremes. So what if I had a super, super, super large specific heat? Well, that would mean it would take insane amounts of energy to change my temperature. So if the specific heat of Y is way, way, way larger than X, you're going to mix the liquid and the temperature is going to be T0 still. So that's how we know it's on that side of the midpoint. So I thought this was a tricky little qualitative, but this is a really fun question in my opinion. A1 is for the checkbox. A2 is some statement equivalent to saying like the heat transfer is the same, where they have the same heat transfer. And then you have to have like a correct statement of what specific heat means. So specific heat is telling you like the energy cost per unit temperature or something like that. So this is how I got the second point. So I imagine this A3 is harder to get because most people would lead with this fact that like the heat transfer is the same. Let's do that. Find the total heat transferred within this process. So what we know is that the Q transferred to X is just the opposite of the Q transferred to Y. Transferred from Y, I should say. So we know that MC delta T for X has to be equal to the opposite of M2C delta T for Y. Alrighty. Then, plugging in, well, we can get rid of the C's. So we get this fact that delta T of X is equal to -2 times the delta T of Y. That already proves our claim is correct, because we see that X increases by twice the amount that Y decreases. So what is delta T for X? Well, delta T for X would be the final temperature minus the initial temperature. And for Y, its delta T would be the final temperature minus its initial temperature, T0. So we can do some algebra here where we'd get TF equals -2 TF plus 2 T0. So we'd get 3 TF equals T0, 2 T0. So TF would be equal to 2/3 of T0. And this actually isn't what we wanted. We do have like another step to do. We have to plug back in because we want the energy transferred in this process. So then we can just do Q from X is equal to MC delta T would be it started at 0, ended at 2/3 T0. So energy transferred in this process is 2/3 MC T0. You can check it works the other way too, because the energy from Y, oh, we're here. We're here and I have so much extra time. Let's do it. M times 2C, because it has twice the specific heat, and its delta T would be final temperature is 2/3 T0, initial temperature is 1 T0, and I'd get -2/3 MC T0. So we see we get equal and opposite sort of heat transfers here, as expected. So how'd you get points? You needed to say Q equals MC delta T, or this fact. So either of these facts gets you B1. To get B2, you had to solve for the correct temperature, 2/3 T0. And for B3, you had to get a consistent substitution. So B3 actually didn't have to be right, because I thought that was a bit unfair to double ding you. So B3 you got by substituting any like correct, according to you, temperature into MC delta T to get the final answer. So if you thought the answer was T/2 was the equilibrium temperature, you could say 1/2 MC T0 and get B3, but not B2. So B2 is really the only like correctness point. B1 is for MC delta T. All right, now we have a little modification. When the liquids are in contact, the entropy of the two liquid system is S0. Once equilibrium is established, the entropy of the two liquid system is SF. Compare these two. Justify referencing thermodynamics. So entropy. We can't do a whole lot with entropy in physics 2, but there's a line in the CED that explains exactly what this is. So what thermodynamics principle is this? You don't need to know this. You don't need to know this is what it's called, but this is the second law of thermodynamics, which says entropy of a closed system can only increase. So anything like that. So we know that this is, you had to state this. So to get C2, you had to state anything that was about entropy or the second law of thermodynamics. So anything that's equivalent to this. And then as a result, we know that the final entropy must be larger. Because entropy, it's not disorder. What even is disorder? Entropy is the tendency of the energy to spread out. So again, think about diffusion. If you just place an air freshener in the center of the room, the particles aren't going to stay there forever. They're going to spread out, and you get to smell that scent throughout the room. So again, that's just some justification. Entropy always increases because energy spreads out. When we combine the two liquids, the energy's spreading out between the two. So that's that. I thought this was a neat question. I thought this was like, it wasn't just trivial. Like there was like this isn't the most common scenario, but it's cool. So I'm expecting good things here. Yeah, that's P2. So like I said, I thought this was a really nice overall exam. Like this was probably my strongest of the practice tests this year. This covers about everything P2 wise. Alrighty.